In this video, we'll be talking about recursion. Okay, so what exactly is recursion? And a lot of computer science students, when they first learn recursion, have a hard time thinking about or understanding this topic. And in this video, we'll try to break it down in its most simplest forms using three key steps. So, first of all, what exactly is the knowledge required that we need to know in order to learn recursion? Well, the only really important thing we need is the understanding of methods or functions. So, in terms of methods or functions, hopefully you've studied your programming language thoroughly to the point that you know about methods and functions. So, what exactly is recursion defined as? Well, recursion is defined as, in our terms, a programming technique where a function calls itself inside its own body. So, that right there is the most simplest version of the definition of recursion. But let's look at exactly how this technique allows us to solve problems. Well, basically, what it does is it breaks problems into smaller and smaller problems, and we'll look at examples later, but essentially, once again, what it does is you have a problem and you know that it has some overlapping features with a smaller version of that problem. So take a problem and break it down into its smaller components to solve the bigger problem. And so in order to do that, what we need to do is we need three key steps. So number one, we need to initialize the recursive call, which is just we need to call it in our main function. Number two, have a base case. In other words, the base case is the most simplest answer or the most simple problem for a given problem. And then number three is the progress to the base case. So we need to somehow get to that base case or that simplest problem, and we need to somehow solve it, right? Okay, so let's look at a very classical version or a classical example of recursion. So this right here is probably the most basic version of recursion. And so as you can see here, we have a void recursion method, and what it does is it just calls the recursion method of itself. So once again, recursion is a programming technique where the method calls itself in its own body, right? So as you can see here, the recursion method is calling itself in its own body. Okay, so let's talk about the three key steps. So number one was initialization. And with initialization, what we need to understand is that in order for the recursion to take place, it must begin somehow, right? A loop doesn't just begin or a problem doesn't begin if it's never asked. So in this case, recursion is our answer or our problem, and we need to somehow ask it first. And so we begin the recursive function call for it to begin, right? We'll use the main method, and we're just going to call the recursion method. And then finally, this is typically done in another function, for example, in a main method or just in any other function, really. Okay, so then the base case. So the base case is also known as the simplest answer for our recursive problem. So we're going to look at more details later, but for now, essentially what we need to understand is that it must end somehow. The recursive method must end somehow. Otherwise, it will continue infinitely, right? So if we have a problem and we just keep asking simpler versions of that problem, well, we never get to an answer that gives us something that's trivial, right? We're just going to keep asking the smaller versions. And how small do we want to get? That's the question, really. And eventually you need to stop. So we need a base case or a simple answer for us to stop. And you might otherwise get time limit exceeded, memory limit exceeded, or a stack overflow error. And so thus, you must set a condition for it to end. So for example, we might have an if statement to end an example that we're going to look at in a little bit. And the third final part is the progression. And this can kind of be thought of as a kind of, recursion. We have a state, and this is the transition uh, to a smaller problem. So this is the progression or the transformation of our current recursive call. Now, in more technical terms, we typically like to call this, with recursion, we have a state, and then we have a, transition. So this is our transition. And so with progression or our transition, what we need to do is we need to reach the base case. You need to progress towards that base case somehow. And otherwise, your recursion will never end, and you're just going to be continuously stuck on the same question forever and ever, right? So why exactly is the classical example that I showed earlier inaccurate, actually? So what's wrong with this example that I showed you earlier? Well, as you can see here, we have the void recursion, and then it calls itself in its own body. And so what are the three things that are wrong with this? Well, number one, there's no initialization. We never really initialize this recursive call, and so it's not very useful in the programming language, in our programming code, right? So there's no point in this recursion method being existent. And number two is there's no base case. So when does this recursion stop, right? It's just going to continuously call itself forever and forever. And then number three, there's no progression, right? So how does it get towards that base case if it exists, if there's no progression? Okay, so those are the three things that are wrong with this. And remember, for any recursive problem, we need to have that progression go towards that base case that we have, and it needs to be initialized, right? It needs to be initially called in order for it to happen. Okay, so let's look at the example, a very common example called factorials. And I'm sure many of you guys have heard of the factorial of a number, but let's look at exactly how it's defined once again. So the factorial of a number n is defined as n times n minus 1 times n minus 2 all the way to 1. So for example, if we had 5 factorial, we might say it's 5 times 4 times 3 times 2 times 1, which is equal to 120. Okay, and so how do we find n factorial using our program, right? Well, one obvious step you can do with a bit of code and a for loop, what you can do is start your for loop at I is equal to 1 and work your way to n, and then keep doing I++. And so we know that that's pretty standard, right? We can multiply some variable that we have globally and return that answer. But how do we do this recursively? And that's our question today. Okay, so we once again know that the factorial of n is the same thing as n times n minus 1 factorial, right? So we know that right there, that's our sub-problem, because once again, recursion is breaking a problem into smaller and smaller problems. And so you can see that right here, we can define factorial of n is equal to n times the factorial of n minus 1. And so with that, what we can essentially see is that we're breaking it into smaller and smaller problems. And so when we call factorial of n minus 1, it's going to be n minus 1 times the factorial of n minus 1 minus 1. So the question is, what is our base case and what is our simplest answer? Well, we know that our simplest answer, if we're going to continue to n minus 1, and we're just going to continuously subtracting 1 from our variable, then we need to progress towards a smaller number. And in this case, our base case, or our most trivial answer, is n is equal to 1, where the answer to when n is equal to 1 is just 1. Okay, So let's look at some code for this, and it kind of writes itself out, right? So we have a function called int factorial, and it passes in an integer n. If n is equal to 1, then return 1, right? That's our trivial case. And otherwise, we should return that n, the factorial of n, right, is n times the factorial of n minus 1. And so let's look exactly what's happening behind the scenes with this stack and everything. So we're going to look at the stack of the code, and we're going to see exactly what's happening in the recursive calls. So initially, we're going to call factorial of 5. And you can kind of think of this as a stack in memory. And in this case, we're kind of going towards, or we're building on top of that stack, right? So with factorial 5, we once again defined it as 5 times the factorial of 4, right? So we're going to be calling factorial of 5 is equal to 5 times the factorial of 4. And now you have to ask yourself, what is the factorial of 4? Well, we define factorial of 4 to be equal to 4 times the factorial of 4 minus 1, which is 3. Like so. And then finally, next we have the factorial of 3. We don't know the factorial of 3, so we're going to ask, what is the factorial of 3? Well, we know that the factorial of 3 is defined as 3 times the factorial of 3 minus 1, which is 2. The same thing applies for 2. We know that that's 2 times the factorial of 2 times 2 minus 1, which is factorial of 1. And there we go. So we see that we finally asked the question, what is the factorial of 1? Well, once again, in our recursive call, we don't find the factorial of 0, right? Because if we had 0, then we would multiply it by 0, and the entire thing would be equal to 0. And so the question is, we should stop now, right? Well, we don't need to search anymore. We don't need to call any more factorials. So what we're going to do is we're going to say that the factorial of 1 is equal to 1. So if you remember in our function there, when n is equal to 1, we just simply return 1. Like so. And now we can finally answer our question, what is the factorial of 2? Where the factorial of 2 is equal to 2 times the factorial of 1, which is equal to 1. So we can finally answer our question of what is the factorial of 2. And now we want to ask ourselves, what is the question, or what is the factorial of 3? Well, we know that the factorial of 3 is 3 times the factorial of 2, which in this case is 3 times 2. And now the question is, what is the answer to the factorial of 4? Well, the answer of the factorial of 4 is equal to 4 times the factorial of 3, which gave us 4 times 6. And then finally, the factorial of 5 asks us, what is the factorial of 5? Well, we know it's defined as 5 times the factorial of 4, which is 5 times 24, giving us an answer of 120. Okay, let's look at another example called the Fibonacci sequence. So I'm sure a lot of you guys have heard of this in mathematics before. It's a very popular sequence of numbers where we kind of define it in a certain way. So let's look exactly what Fibonacci is first before we delve deep into it. So the Fibonacci sequence is defined in a mathematical way as fib n is equal to 1 if n is equal to 0, 1 if n is equal to 1, and otherwise, if n is greater than 1, it's defined as fib of n minus 1 plus fib of n minus 2. So it's basically the sum of the previous number and the sum of the previous number. And depending on your definition, we might start at 0, we might start at 1, but in this case, I'll start at 1. Okay, so the sequence will look something like this, where we have 1, 1, 2, 3, 5, 8, 13, 21, 34. And you can see that it's the sum of the two previous numbers, right? So 2 is the sum of 1 and 1. 3 is the sum of 2 and 1, 5 is the sum of 2 and 3, 8 is the sum of 3 and 5, 13 is the sum of 5 and 8, 21 is the sum of 13 and 18, 34 is the sum of 13 and 21, and this continues on forever. And so to find the nth Fibonacci number, we just need to make this simple recursive call. We need to say int fib, where we pass in an integer n, and what we're going to have is our base case, right? We're going to have if n is equal to 0 or n is equal to 1, then return 1. And otherwise, what we need to do is return the sum of the two previous numbers, which is defined in fib of n minus 1 and fib of n minus 2. Okay, so you can kind of see how the code kind of writes itself out, because recursion is kind of just thinking about what is the formula for the nth number, and does it reoccur in a previous instance of a smaller problem? Okay, so next, let's look at exactly how this Fibonacci call works. So let's say we called fib of 92. So that's a pretty big number. And what's going to happen is it's going to call the two previous numbers. So we're going to have fib of 91 and fib of 90. So first, let's actually call fib of 90. So with fib of 90, what's going to happen is that it's going to call the smaller problems from there. So it's going to call fib of 88. And from fib of 88, that's going to call fib of 86. And then it's going to continue on and on and on until we reach our base case where fib of 1 or 0 is equal to 1. Okay, and then it's going to work its way back up, back to fib of 86, and we're going to have to calculate fib of 85. And that's going to be on the right side, for example. Once it's calculated all of that branch, we'll get the value for fib of 86. Then what it's going to do is it's going to call the function, go back to the function for fib of 88, because we have one of the components for fib of 88. Then it's going to call fib of 87, calculate all its values, go back to fib of 88, and now we finally successfully calculated fib of 88. Then we need to calculate fib of 90 again, and we need to finish it off. So we need to calculate the fib of 89. That's going to call the fib of 87. It's going to finish off its branch another time, sorry. Go back to fib of 88. Call the, fib of, for example, 86, fib of 87, and then retrieve its answer and put it back into fib of 89. And as you can see, fib of 90 has retrieved its answer from both fib of 88 and fib of 89 now. So that one's done. And we finish our left branch of fib of 92. Then we're going to do the exact same thing for fib of 91. Call this function right here. Go all the way down. Come back up. Call fib of 90. It's going to call fib of 88, as well as fib of 89. Calculate those values, work our way back up, and it's essentially just telling the answer of its previous, parent. And so finally, when we get fib of 92, we're going to call fib of 90 and fib of 91. And that's pretty much it. Okay, so now let's look at exactly how we might implement, and I'll show you step by step how to implement the Fibonacci and the factorial. So first I'm going to implement the factorial with you guys. So for the factorial, what we're going to do is we're going to see that we're going to have to import some kind of Java utility. And this really depends on whether you want to take input or not. So in this case, I might want to take an input and see the different types of numbers that I can get. Then what I'm going to do is I'm going to create my class, and then I'm going to write my main method here. Okay, from there, I'm going to create a scanner object so that I can take an input. And what I'm going to do is I'm going to say, for example, I want the nth Fibonacci number. So I'm going to take that as input, and I'm going to return it. So I want to write system.out.println the factorial of the number n. Okay, so then what we're going to do is we're going to create a method up here. And what it's going to do is it's going to return an integer. And that integer is my nth factorial, right? So it's going to return an integer. So that's my return type right here. And I'm going to pass in the integer n. And once again, for factorial, the base case is if n is equal to 1, then let's simply return 1, because that's our most trivial case. We know that is obvious, right? And then otherwise, we should return the factorial of n is equal to n times the factorial of n minus 1. And that's pretty much it. So if we take, for example, the number 5, right? I'm expecting an output of 120. So let's see if that's true or not. And there we go. So as you can see here, we've finished it off and we have an accepted answer of 120. And this can, go on to all sorts of values, right? As long as the answer fits within the integer data type size. Okay, let's look at another example called the Fibonacci. So let's take an input again. And let's say I wanted the nth Fibonacci number. And this n is going to start at 0. So what I'm going to do is, once again, I'm actually going to write system.out.println, and I want the Fibonacci of the nth number. Right, what is the nth Fibonacci number? And so here what I'm going to do is I'm going to create a function called fib, pass in a number n, and once again we know our base case. We know that if n is equal to 1 or n is equal to 0, return 1. And then otherwise, we know that it's defined as fib of n minus 1 plus fib of n minus 2. Okay, so if we write down our sequence right here, we know that it goes 1, 1, 2, 3, 5, 8, 13, 21, and then so on. And let's say we wanted to calculate the 1, 0, 1, 2, 3, 4, 5, 6, 7th Fibonacci number. We're expecting a 21. So let's see if that works. And as you can see, we get a 21. Okay, so in this video, you basically learned about recursion and 2 very simple examples that you might see in a very useful application.